Now let's see some properties of Z transform and some theorems. First is called shifting to the right. What is shifting to the right? Let's say we have this signal, continuous signal, like this. Okay, this is, let's say, pi. So you know, if this signal is ft, you have ft minus t0. Let's say this is t0, will be, this is shifted to this point, t0. This is shifting to the right. Similarly, if you have discrete signals, let's say your signal is, this is 0, this is 2, 1, this is 4, like this. If you have to shift it by 1, this is your un. So what you want is un minus 1. So what will happen? At 0, this is this. It will be at 1. Then second will be 0. Then this. So this is shifting to the right. Okay. This is the meaning of this. How we do? If let's say your signal is un and Z transform of un is uz. These are our usual notations. So then un minus k, this will be shifting to the right by this k, by k. So Z transform of this is basically Z to the power minus k uz. This is how we shift the discrete signal to right. Now the proof is very simple, but that is not what we need to discuss. We'll use this and solve problems. We'll see how to analyze functions using this property. So this is shifting to the right. Similar to that, we have shifting to the left. How we shift to the left? It is t plus t0 or n plus k. I explained to you what is t minus t0, n minus k. Similarly, if you shift to this side, that is your signal is, let's say, this one, and you want to shift it to this side, to this point. So what you will do? Your signal will be like this now. So it is shifting to the left. This is continuous. Similarly, we have for right, sorry, for discrete signals. So what we do is shifting to the left. This will be your second property. So that will be Z of un plus k. Okay. So how to get this? This we get Z to the power k into u of z minus u0 minus u1 z minus 1 minus u2 z minus 2 up to the point where you have minus u k minus 1 z. This is 2 minus 2, so this will be k minus 1. Okay, so this is how we shift to the left. Okay, some important results. Let's do it now. What will be for un plus 1? These are some very important results, very frequently used results. Not, I shouldn't say important, frequently used. So Z of un plus 1, that will be, see, Z, k is 1, Z, this will be uz and minus u0. Why? Because this is plus 1 only. When you put 1 here, it is gone. See, if you put 1, k equal to 1, this is k equal to 1, so k equal to 1 means u0 and this is 0. When k is 1 only, this will be u0. Okay, so this is u0, it cannot be 1, that is, this won't come into this. So this is z un plus 1. What is z un plus 2? It will be z to the power 2 uz minus u0, then 2 minus 1 1, so u1 z to the power, this will be 2 minus 1 1, so 1, and then 2 minus 1 0 again. So this, similarly for un plus 3, it will be z3 up to this point, u2 point. Clear? So these are the two properties. Let's see example to understand this. Let's say we have to find our un is 1 by factorial n plus 1, then our un is 1 by factorial n plus 2, also un is 1 by factorial n minus 1. Okay, so looking at the questions only, you understand that if we are able to get the value of un equal to 1 by factorial n, this we'll be able to find these values using shifting properties. So what is, sorry, not to n. So what is z 1 by factorial n? It will be from our basic definition, n equal to 0 to infinity. 1 by factorial n z minus n. So if you expand it, n equal to 0, this will be 1, this will be 1. So 1 plus n equal to 1, this will be 1, z minus 1. That is z minus 1 by factorial 1, then z minus 2 by factorial 2, and so on. What is this expansion? If you remember this expansion, it is the expansion of e z minus 1. That is e to the power 1 by z. So we know that z transform of 1 by factorial n is e 1 by z. So let's see what are these values. Let's start with that. Z transform of 1 by factorial n minus 1. You have seen that Z transform of un minus k is basically z minus k uz. So we'll put it, k is 1 here, so it will be z minus 1 and then uz, that is e to the power z minus 1. So this is the answer. Okay, so first one we have the result. Second, we have to find 1 by factorial n plus 1. This, if you remember, it is n plus k. So it is z to the power k, that is z to the power 1, and here we have uz minus u0. This is the value. So it is z, uz is e to the power 1 by z minus u0. What is the value of u0? So u0 is 1. If you see this expansion, the expansion of, if you remember, the expansion was 1 plus z minus 1 by factorial 1, z minus 2 by factorial 2. So this is your u0, this is your u1, and so on. So u0 is 1. So this is the value. When you have to take n plus 2, what was it? It was z to the power 2 uz minus u0 minus u1z, this. Okay, so what is u1 is also 1. We have seen 1 z by factorial 1, z minus 1 by factorial 1. So this is 1, this is 1. So what you get is z square e to the power 1 by z, then 1 minus z minus 1. This is the result. Okay, so I guess this is shifting property is very easy. You'll be able to solve the questions without any problem. Now let's see how to find u0, u1, u2, u3. This was a simple expansion, so we were able to find u0, u1. What if it is complex? So for that we have two theorems. First is called initial value theorem. Initial value theorem. What is initial value theorem? It states that if z transform of un is uz, this is our usual notation. So for this we have u0, the first term, that is equal to limit z tending to infinity uz. This is your initial value theorem. You can see the proof in any book. That is not of our concern here. We have to understand the concept and we have to analyze functions. Then similar to this you have u1, that is limit z tending to infinity. You had seen, what was it? N plus 1. So it is z uz minus u0. This series you know. Similarly, you want to take u2, it is limit z tending to infinity. This would be z square uz minus u0 minus u1 z minus 1. Then u3 will be limit z tending to infinity z cube uz minus u0 minus u1 z inverse u2 z minus 2. So this way you find u0, u1, u2, u3. This is called initial value theorem. Okay, and then we have final value theorem. What it is? The final value theorem is, if our z transform of un is uz, then limit n tending to infinity of un is equal to limit z tending to 1 z minus 1 uz. This will be very helpful in solving problems. This is final value theorem. We'll see example and understand this. Okay, you should learn it by heart. Limit of un when n tends to infinity is limit of z minus 1 uz when z tends to 1. Okay, let's see example to understand. So our question is uz is 2z square plus 5z plus 14 z minus 1 to the power 4. We have to find u0, u1, u2. Now you saw u0 is what? It is limit z tending to infinity of uz. This is your initial value theorem. We have to take z tending to infinity of this. So let's write it here. 2z square plus 5z plus 14 z minus 1 4. Now you know you all have solved limit and continuity questions in calculus. What we do? We try to find out when the limit is to infinity, what we do? We try to put this particular variable in the denominator. So how it can be done? See, if we take z to the power 4 out of this, let's say I take z to the power 4 here. So what I'll get? I'll get 1 minus 1 by z here. Clear? Now z to the power here, this is z square. So what we can do? We can take 1 z square this side and then 1 z square we divide by this. So this z to the power 4 is distributed. This is this and this. So what do we get? I'm writing here. Limit z tending to infinity. It is 1 by z square. You see z square. 2 plus 5 by z. 2 plus 5 by z plus 14 by z square by 1 minus 1 by z to the power 4. Now when you put infinity, this is 0, so this is 1. This is 0, this is 0. So this is 2 by z square. So 2 by infinity, that is 0. So this limit is 0. Okay. Now let's see 1. u1. What is u1? Limit z infinity. It is, if you remember, it is given as this uz minus u0. Okay. But u0 is 0. We just saw. So this is 0. So it is z uz. See, this is 1 by z square. So if you multiply it by z, this will be 1 by z and 2 by z. When z tends to infinity, again it is 0. Okay. Now let's see the next one. What when we have limit z tending to infinity? This will be z square uz minus u0 minus u1 z minus 1. This is the case. Now u0 and u1 both are equal to 0. So this is gone. So you have z square into uz. So z square into uz is this gone. Now what do you have? 1. If you multiply this by z square, so this is 1. Now when z tends to infinity, what is left is 2. So the answer is 2. Okay. So this way we can use initial value theorem to find u0, u1, u2, these values, initial values. Okay. Let's see one simple example to understand final value theorem. What was final value theorem? It was limit n tending to infinity un is equal to limit z tending to 1 z minus 1 into uz. This is your final value theorem. So what is this? Limit n tending to infinity. This is u infinity. So this is this. So we have to find u infinity for this. What it will be? Z minus 1 into this. So what you get? See, this will be z minus 1 into 2z square plus 3z plus 2 by z square minus 1. So we can write it like z plus 1 into z minus 1, z square minus 1. So this cancels. Now you put the value of z. It is 2 plus 3 plus 2 by 2. So it is 4, 3, 7, 7 by 2. Okay. So this way we use initial value theorem and final value theorems to find the values of k equal to 0 to infinity. Okay. Now let's see one more property. This is very handy. Multiplication by n square and so on into the power m. You have any function un, if it is multiplied by n or n square. We have seen it in the starting also, how to get these values. Now we'll have another way to solve it. Initially what we used to do was multiplying by n to the power p That was another way. Now let's see if the multiplication is like this, what we do. So z of n to the power u, n into un, if you multiply un by this, and z of un is uz, so it is simply minus z d by dz of uz. Okay. Now, if you have n square un, it is minus z d by dz 2 times of this function. That is, you'll take one time, you'll take this. What is the meaning of this? One time you'll take this, and then again, that is like this, z by dz of minus z by d dz of uz. So this is the meaning. Okay, you take 2 times. Similarly, if this is n to the power, let's say k of un, then what you do is very simple, d by dz k times. K times you will do this process. So this is very simple. Let's see how it is. Does it makes calculations easier? Let us see. We know z transformation of 1 is z by z minus 1. This we know. Now, let's say we want to know z transformation of n. What it can be? Earlier we had used that particular way. Now, using this way, it will be minus z d by dz of u of 1. Okay. So u of 1 is, this is n into 1. So u of 1, what it would be? This will be this. Okay. So let's find out. This will be minus z. This is z minus 1 dz by z minus z by z minus 1 square. So this is, and minus minus gone. So what you get is z by z minus 1 square. Okay. So very easily we are able to find the value of zn, which is equal to z by z minus 1 square. Okay. Now we have to, let's say we have to find z of n square. What will do? I told you z by d by dz 2 times of uz. That is minus z d by dz of minus z d by dz of uz. We just did it. What we got? We got z by z minus 1 square. Okay. So we have to find this. Let's find the derivative of this. It will be minus z. This will be z minus 1 square, and you have dz minus z into, it will be 2z minus 1, and this will be z minus 1 square. Oh, sorry, 4. It is already square. So let's see. It will be minus z. This is, see, I'm writing here, z square plus 1 minus 2z from here. Then this is minus 2z square, minus 2z square, and then minus minus plus 2z. So 2z cancel, this by z minus 1 to the power 4. What you get in the numerator? It is minus z, see, 1 minus z square by z minus 1 to the power 4. Or if we put this z here, sorry, plus here, what you will get is z square minus 1. Okay. Then this z square minus 1 can be written as z plus 1 into z minus 1. So this cancels this, this becomes this. So this is z plus 1 by z minus 1 cube. So this way we are able to find different results. Clear? Now let's see a complicated one. We had seen, if we take e to the power minus in theta, using that we were able to find the value of z of cos n theta and z of sin n theta. This was what, if you remember, z of cos n theta and z of sin n theta. So this was z sin theta by z square minus 2z cos theta plus 1, and this was z square minus z cos theta by this. Okay. So what if we have to find z of n sin n theta? So you know this will be minus z d by dz of uz, where uz is z sin theta by z square minus 2z cos theta plus 1. So this is easy because theta is constant, the derivative is dz. This will be this. Here you have z square minus 2 z cos theta plus 1. This is sine theta. Then you take z sine theta. What you get is 2z minus 2 cos theta by square of this, z square minus 2z cos theta plus 1 square. Okay. Now let's multiply this. Minus z, this is z square sine theta, z square sine theta. Then this is minus 2z sine theta cos theta. Then you have sine theta. Here you have minus 2z square sine theta. Then plus 2z sine theta cos theta. So this cancels this by this square. Let's say denominator square. So what we get is minus z into this cancels. So what we get is, see, 2z square z square. So it is in minus side and we have sine theta. So it is sine theta minus z square sine theta. Z square sine theta by square of this. So finally what we can get, or what we will get is, we can take sine theta out and z here. So this will be z sine theta. Okay, we have taken sine theta out. So this will be z square minus 1. Okay, and by this z square minus 2 z cos theta plus 1. The calculation takes time, but it is easier. So I have found the value for z n sin n theta. What you do? You know what is z cos n theta? You find the value of z n cos n theta. Z n cos n theta. This is your task. Do it.